Imagine this, a visitor from another star system, tearing itself apart just millions of kilometers from the sun. This isn't science fiction. This is happening right now in our celestial backyard. The object is known as 3I Atlas, only the third confirmed interstellar object ever detected, and it has just unleashed jets of gas and debris stretching a staggering 3 million kilometers into the void. To grasp that scale, picture the distance from the Earth to the Moon. Now multiply it by 8. We are not talking about a little puff of gas from a typical comet. We are talking about structures so massive they dwarf planetary distances, erupting from what should be a relatively small chunk of ice and rock. When scientists first saw these images, the immediate question wasn't just, what is this? It was, what the hell happened? And now a troubling question lingers in the minds of everyone who sees the data. Did it simply break apart under the immense strain, scattering alien material across our solar system? Or is this a deliberate maneuver by something we don't yet understand? Something artificial? Tonight, we dive headfirst into the mystery, the jaw-dropping science, and the staggering possibilities. Scientists assure us there is no direct danger to Earth, but by the end of this journey, you will see the existential ripples this visitor could send our way. The story of 3I Atlas is not just about astronomy. It's about our place in a cosmos that is far stranger and more active than we ever dreamed. Stay with us, because what happens next is something no one prepared us for. If this mystery has you hooked the way it has me, I want you to be part of this investigation as it unfolds in real time. Where are you watching from right now? What time is it there? Drop a comment below and let me know. Make sure you hit that subscribe button and ring the bell so you don't miss a single update. If you want to help this community of curious minds grow, share this video on X, Facebook, Reddit, or even in your group chats. You are the reason we can keep chasing stories like this, so thank you for having our back. Let's begin at the beginning. The day the sky changed. It was November 9th, 2025. A group of astronomers, working with a series of deep space photographs stacked together to reveal faint details, saw something that shouldn't exist. Stretching from a single point in the darkness were two enormous, symmetrical jets of material. One reached roughly 1 million kilometers, the other even farther. The object at the center of this impossible display was called 3I Atlas, and in that moment, it became the most confusing thing in our solar system. You need to understand something about the scale here. 3 million kilometers is about 8 times the distance from Earth to the Moon. This isn't a subtle anomaly. This is a cataclysm happening in near real time, a spectacle of force and energy that defies all our expectations of what a comet should be. I Atlas is only the third confirmed interstellar object ever detected entering our solar system. Pause and think about that for a moment. In all of human history, with all our telescopes and all our sky surveys, we have only confirmed 3 visitors from beyond our cosmic neighborhood. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked 1,000 debates about its origins. The second was 2I Borisov in 2019, which, while foreign, at least behaved like a proper comet. And now we have this. Discovered on July 1st, 2025, by the Atlas survey operating in Chile, its trajectory told astronomers immediately that this wasn't one of ours. The orbit was hyperbolic, meaning it came from interstellar space, fell toward the sun, and would eventually leave our system forever, never to return. It wasn't bound to our star like the comets and asteroids that were born here billions of years ago. This thing came from somewhere else entirely, carrying with it the chemical fingerprints of another stellar neighborhood, another time, another formation process we can only guess at. Early estimates from Hubble Space Telescope images suggested the nucleus, the solid core of 3I Atlas, measured about 5.6 kilometers across. That's already enormous for a comet. For comparison, Halley's Comet, probably the most famous comet in human culture, has a nucleus roughly 11 kilometers long, but is much less massive overall. But here is where things start to get strange. Other data suggested 3I Atlas might actually be larger, perhaps significantly so. The numbers weren't adding up, and that was before anyone realized just how weird this object truly was. Under normal statistics, under the models we use to predict how many interstellar objects should pass through our system, something this large should be incredibly rare. We're talking about odds so low that detecting one in a human lifetime should be a monumental surprise. And yet here it was, big enough to see, bright enough to track, and already behaving in ways that made seasoned astronomers start using phrases like unprecedented and inconsistent with known models. Then came the key turning point. 3I Atlas passed perihelion, its closest approach to the Sun, around October 29, 2025. Perihelion is when comets typically brighten and become active as solar heat vaporizes their ices and creates the familiar tail. But what happened to 3I Atlas wasn't familiar at all. Shortly after perihelion, observers started seeing those massive jets, that bizarre twin plume structure, and a cascade of changes that suggested something fundamental had shifted inside the object. So here is the core question, the one that is keeping scientists awake at night and filling preprint servers with speculative papers. What if 3I Atlas didn't just get bright and active near the Sun? What if it actually fragmented, broke apart under the stress of solar heating and tidal forces and internal gas pressure? What if we are looking at the wreckage of an interstellar visitor, shattered into pieces, spilling its alien guts across millions of kilometers of space? If that's true, if it really did break up, then we have just been handed an extraordinary gift. Fragmented material means increased surface area, which means more stuff exposed to our telescopes and spectrometers. We could be looking at the interior composition of an object formed around another star potentially billions of years ago, processed by cosmic rays during eons of interstellar travel, now laid bare for us to study. It's like an alien autopsy, except the body is millions of kilometers wide, and we are the detectives trying to piece together what killed it. But there is another possibility, one that is quieter in the official papers, but louder in the hallways and the blog posts. What if it didn't fragment? What if 3I Atlas is still intact, and those jets, that energy, those impossible numbers, are being produced by something other than passive ice sublimation? What if we are looking at propulsion? What if we are looking at technology? That is not a mainstream conclusion yet. It is not even a widely accepted hypothesis, but it is on the table, and it is there because the data refuses to fit neatly into the box labeled normal comet. When your observations require either a radical rethinking of comet physics or a consideration of artificial origins, you are in uncharted territory. You are in the kind of territory where science meets philosophy, where discovery meets dread. We care about this because the implications branch in every direction. If 3I Atlas shredded, we gain unprecedented access to interstellar matter. We refine our models. We learn about how objects survive the journey between stars. If it didn't shred, if it's doing something else, then we might be looking at the first confirmed technological artifact from beyond our system. And if that's true, everything changes. So what happens next? What happens to us, to Earth, to our understanding of the cosmos if this interstellar visitor really did break apart near the Sun? Or perhaps more unsettlingly, what happens if it didn't? The answers lie in the data, and the data is stranger than anyone could have imagined. Let's talk about what the telescopes actually saw, because the devil here is absolutely in the data. After perihelion, observers worldwide started capturing images of 3I Atlas that looked nothing like a standard comet. The twin jets were the headline, sure, but there was more, subtle details that pointed to a deeper chaos. The tail structure kept changing, day by day, sometimes hour by hour. Amateur astronomers were posting images online showing what looked like plumes, like the object was smoking, puffing out material in irregular, violent bursts rather than the steady, predictable outgassing you'd expect from solar heating. It wasn't melting gracefully, it was convulsing. Then there was the color issue, a visual clue that something was fundamentally off. Comets generally appear whitish or slightly yellowish because they reflect sunlight and emit light from glowing gases. 3I Atlas at certain points turned bluer than the Sun itself. Not just a little blue, but measurably, significantly bluer, and the color kept shifting, changing over days and weeks in ways that didn't correlate neatly with its distance from the Sun or any predictable heating curve. It was as if the object was cycling through different modes, different states, as if someone or something was flipping switches on its surface, changing the very nature of the light it emitted. This wasn't passive reflection. It was dynamic, almost behavioral. Spectroscopy, the powerful technique of splitting light into its component wavelengths to identify chemicals, revealed the next layer of strangeness. The James Webb Space Telescope and the SphereX mission both turned their sensitive instruments toward 3I Atlas and found a coma, the cloud of gas surrounding the nucleus that was absolutely dominated by carbon dioxide. The ratio they measured was stunning. Carbon dioxide to water was roughly 8:1. For context, most solar system comets have ratios closer to 110, or even 1 to 100. Water ice is usually the main event, the primary volatile that drives activity. Here, carbon dioxide was the star, and water was barely a supporting actor. This flipped script matters immensely because it changes the entire energy budget of the object. Carbon dioxide sublimates, turns from solid to gas, at different temperatures and rates than water ice. It also requires a specific amount of solar energy to drive that sublimation. The very engine of this comet was alien. When scientists ran the numbers, when they calculated how much carbon dioxide 3I Atlas was spewing out, they ran into a brick wall of a problem. The surface area required to produce that much gas, given reasonable assumptions about solar heating and sublimation efficiency, was enormous. We're talking about an effective absorbing surface area exceeding 1,600 square kilometers, which corresponds to a spherical object roughly 23 kilometers in diameter. But the observed size, remember, was about 5.6 kilometers. The math didn't work. It was a fundamental discrepancy. Either the object was much, much larger than the Hubble images suggested, or the model of how comets sublimate was fundamentally broken, or something else, something entirely different, was going on to produce that vast volume of gas. The mass loss rate added another layer of profound confusion. Preliminary estimates suggested 3I Atlas was losing roughly 5 billion tons of material per month. Let that number sink in for a second. 5 billion tons. Every month. The outflow velocity was pegged at about 0.4 kilometers per second, which is fast, but not absurdly so for sublimating gas, except the rate of mass loss wasn't steady. It was accelerating, and accelerating steeply. Early in its approach, the object was losing maybe 150 kilograms per second. Within a few weeks, that figure skyrocketed to 2 million kilograms per second. That's an increase of over 10,000 times. To explain that kind of violent acceleration with standard comet physics, you need a distance to Sun power law of around 10.5. That number is absurdly steep. Most comets follow power laws between 2 and 4. A value of 10.5 is off the charts, in a territory that suggests the rules themselves no longer apply. What does that steep power law mean in practice? It means the object's activity was far more sensitive to solar distance than any normal comet should be. It means either the composition is so wildly different that our physics doesn't apply, or the physical structure changed dramatically and suddenly. Or the physics at play isn't purely about solar heating anymore. It's the kind of number that makes scientists pause, pour another coffee, and double-check their calculations, because if it's real, it's pointing at a phenomenon we don't fully understand, a process we have never witnessed before. These anomalies don't exist in isolation. They cluster together into a picture that refuses to resolve cleanly. High carbon dioxide, insufficient surface area, extreme mass loss acceleration, bizarre color changes, and finally, non-gravitational acceleration. This last one is critical. It means the object's trajectory was being nudged, pushed, by forces other than just the sun's gravity. This is usually explained by asymmetric outgassing, where gas shooting off one side of the nucleus acts like a tiny, natural rocket thruster, altering its path. All of these anomalies could individually, with enough effort, be explained by stretching existing comet models to their breaking point. But together, they form a pattern of weirdness that strains credibility to its limit. It's a chorus of inconsistencies, and the song it's singing is one of profound mystery. The data is real. The observations are solid. Multiple independent teams using different instruments are seeing the same anomalies. This isn't a case of bad calibration or a single rogue measurement. 3I Atlas is genuinely behaving in ways that push the boundaries of what we can model with known physics. We're at the edge, looking into a space where either our understanding of comets needs a major, foundational update, or we're seeing something that isn't a comet at all. To truly appreciate how strange 3I Atlas is, you first need to understand what normal looks like. We need to establish the baseline, because what we expected and what we got are two different realities. A standard comet is essentially a dirty snowball, a leftover chunk of ice and rock from the early solar system, a pristine relic frozen in time. As it approaches the sun, solar radiation heats the surface, causing volatile materials, mostly water ice, to sublimate directly from solid to gas. This outgassing creates a hazy, glowing cloud called the coma. The pressure of sunlight and the solar wind then pushes that gas and dust away from the sun, forming the characteristic tail that can stretch across the sky. It's a passive process, almost elegant in its simplicity, entirely driven by external energy from the sun. The The comet itself doesn't do anything. It just sits there and melts according to predictable, well-understood rules. Typical solar system comets have compositions that reflect their birthplaces. They formed in the cold outer reaches of our planetary system, in the Kuiper belt or the distant Oort cloud, where water ice was the most abundant volatile material. You get water as the dominant gas, with smaller, trace amounts of carbon monoxide, carbon dioxide, methane, ammonia, and other simple molecules. When scientists measure the gas coming off these comets, the ratios are predictable. Water leads, everything else follows. The behavior is also predictable. The comet's brightness increases smoothly as it gets closer to the sun, following a reliable curve. The tails grow and shift direction based on the changing angle to the sun and the flow of the solar wind. There might be occasional outbursts if a pocket of gas suddenly vents, but overall, it's an orderly, almost clockwork process. Now, place 3I Atlas next to this picture of normalcy. The carbon dioxide dominance is the first glaring red flag. The ratio is flipped on its head. Instead of water leading the charge, you have carbon dioxide at 8 times the water abundance. That's not just unusual. That's a complete inversion of the normal pattern. It screams, that this object formed in a very different environment, somewhere much colder or much richer in carbon dioxide ice than anything we know of in our solar system. Or it suggests the surface has been chemically altered, cooked and processed by cosmic rays over millions of years, in a way we don't see here at home. This isn't a minor variation. It's a fundamental difference in origin and history. Then, there's the sheer mind-boggling scale of the jets. Most comets produce jets, sure, but they're relatively modest, extending maybe a few thousand to tens of thousands of kilometers. 3I Atlas is producing jets that stretch for millions of kilometers. The comparison isn't just a matter of degree, it's a difference in kind. It's like comparing the gentle flow of a garden hose to the blast of an industrial water cannon mounted on a dam. The volume and velocity of material being expelled is orders of magnitude higher than anything a typical comet, even a large one, can manage. This isn't sublimation, it's eruption. The tail structures are also bizarre and unpredictable. Comets usually have 2 distinct tails, a dust tail and an ion tail, and they point in roughly predictable directions based on solar wind and radiation pressure. 3I Atlas has shown multiple shifting tails, changing configurations, structures that appear and disappear within days, and an overall morphology that seems to change at will. It's as if the object can't decide what kind of tail it wants, or as if multiple, competing processes are fighting for control of its appearance. It is dynamic in a way that feels chaotic, not orderly. Let's return to the nuclear size problem, because it's central to understanding the gap between expectation and observation. If you want to sublimate enough carbon dioxide to produce the observed jets and the immense coma, you need a certain amount of surface area exposed to sunlight. The calculations are straightforward physics. You take the solar flux at the comet's distance, multiply by the surface area, factor in how efficiently carbon dioxide absorbs that energy and sublimates, and you get an expected mass loss rate. When scientists did this math for 3I Atlas, the required surface area implied an object far larger than what the Hubble images showed. The numbers demanded a giant, but the pictures showed a mere large comet. This is the core contradiction. Fragmentation offers a potential way out of that paradox. If the nucleus broke into many smaller pieces, each piece has its own surface area. Add them all up, and you could get the necessary total area without needing a single, giant nucleus. It's like shattering a large boulder into a pile of gravel. The total mass is the same, but the total surface area is much, much higher because all those little pieces have their own exteriors. More surface area equals more sublimation equals bigger jets. The hypothesis fits neatly, but does it fit perfectly? Not quite. Fragmentation should produce observable signatures. You should see distinct multiple nuclei, separate bright spots, separate sources for the jets. Observers have been looking, and while the data is messy and the object is far away, there's no clear consensus yet on whether we're seeing one nucleus or 16. Some analyses suggest multiple sources, others suggest a single, incredibly active core with violently asymmetric outgassing. The ambiguity is frustrating for scientists who crave clean answers. And then there's the alternative, the one that doesn't rely on natural breakup. What if 3I Atlas isn't behaving like a normal comet because it isn't a normal comet? What if those jets are exhaust from a propulsion system? What if the color shifts are thermal signatures from active systems cycling on and off? What if the non-gravitational acceleration is a deliberate, tiny course correction? That's speculation, absolutely. But it's speculation driven by the data's stubborn refusal to fit neatly into any natural box we have built for it. To use an analogy, imagine you find a bird flying over your house. You expect it to flap its wings, glide, maybe soar on thermals. Now imagine this bird is glowing electric blue, shooting fire from its tail, and moving at 300 kilometers per hour in a perfectly straight line with no visible means of propulsion. At some point, you stop trying to explain it as a weird bird and start considering that maybe it's not a bird at all. Maybe it's a drone. Maybe it's something built. 3i Atlas is our glowing blue bird. The expectation was a comet. The observation is something that stretches the definition of a comet to the breaking point. Either it's a comet doing things we've never seen a comet do, in which case our models need serious, fundamental revision, or it's something else, in which case our models are fine, but our assumptions about what's out there and who might be out there just got shattered. Let's explore the safer, more conventional path first. Let's give the universe the benefit of the doubt and assume that known physics, pushed to an extreme, can explain what we're seeing. This is scenario A, the violent breakup. Imagine you're a 5-kilometer ball of ice and rock that has spent millions, perhaps billions of years drifting through the unimaginable cold and emptiness of the galaxy. You've been irradiated by galactic cosmic rays, bombarded by micrometeoroids, and chilled to near absolute zero for longer than human civilization has existed. You are a primordial relic, a time capsule from another star. Now, your long journey has brought you into a new solar system, and you are falling faster and faster toward a star. And that star is pumping energy into you at a rate you've never experienced. Your surface starts to heat rapidly. Your ices begin to sublimate violently. Gas builds up under your crust. The pressure increases. At the same time, the tidal forces from the star's gravity start pulling harder on your near side than your far side, stretching you. Something, eventually, has to give. That's the natural fragmentation hypothesis in a nutshell. Under the extreme conditions near perihelion, 3i Atlas could have simply cracked apart. The combined stress of intense solar heating, the internal gas pressure from rapidly sublimating volatiles, and the tidal gradient from the sun's gravity could have combined to exceed the object's structural strength. It's crucial to understand that comets are not solid monoliths of rock. They are rubble piles, loosely bound collections of smaller chunks, boulders, and dust, held together by their own weak gravity, and maybe some ice, acting as a glue. Hit them with enough stress and they come apart. We have a famous precedent for this right here in our solar system. The most famous example is comet Shoemaker-Levy 9, which broke into at least 21 distinct fragments after passing too close to Jupiter in 1992. Those fragments then famously collided with Jupiter in 1994, creating spectacular impact scars visible even in small telescopes. Jupiter's immense tidal forces ripped Shoemaker-Levy 9 apart, and while 3i Atlas isn't dealing with Jupiter's gravity, it is dealing with intense solar heating and a close perihelion passage that could produce similar disruptive effects. If 3i Atlas did break up, the fragments would begin to spread out along the object's orbit, creating a long, diffuse trail of debris. The pieces would separate over time, moving at slightly different speeds due to their different masses and the varying rocket effects from their individual outgassing. You'd end up with something like a string of pearls, dozens or hundreds of kilometers long initially, eventually stretching to millions of kilometers as the fragments diverge over weeks and months. Each fragment would have its own surface area exposed to sunlight. This is the key to solving the energy budget problem. Breakup dramatically increases the total surface area for a given mass. Think of it like crushing an ice cube versus leaving it whole. The crushed ice melts far faster because more of it is exposed to the warm air. The same principle applies here. More surface area means more sublimation, which means more gas production, which means bigger, brighter jets, and a more active, expansive coma. The observed surge in activity after perihelion fits perfectly with a fragmentation event that suddenly multiplied the effective surface area available to the sun's heat. A.V. Loeb, the Harvard astrophysicist who has become a prominent and often controversial voice in the discussion around interstellar objects, suggested in one of his blog posts that 3i Atlas might have fractured into at least 16 significant pieces. That number comes from trying to reconcile the observed activity levels with the required surface area. If you need 16 times more surface area than a 5.6 kilometer sphere provides, then you need roughly 16 fragments of comparable size, or many more smaller ones. The math is approximate, but it gives you a sense of the scale of the proposed disintegration. We're not talking about a little crack or a chip coming off. We're talking about a wholesale, catastrophic disintegration of the entire body. What would that mean for Earth and the inner solar system? Let's start with the good news. There is no collision threat. None. 3I Atlas is on a hyperbolic trajectory that does not intersect Earth's orbit at any point. The object came from interstellar space, swung around the Sun, and is heading back out into the galaxy. Even if it broke into 1,000 pieces, those pieces are all following roughly the same path, and that path doesn't come anywhere near us. The closest approach to Earth is scheduled for December 19, 2025, but even that is millions of kilometers away, far beyond the Moon and far beyond any conceivable danger zone. The less good news, though it's still not threatening, is that fragmentation does produce a lot of dust and small debris. That material spreads out, gets pushed around by solar wind and radiation pressure, and forms a diffuse, elongated cloud along the orbit. If Earth happened to pass through a dense part of that cloud, we might see some extremely weak meteor activity, like a very faint meteor shower, with tiny particles burning up harmlessly in the upper atmosphere. Space-based instruments, satellites, and telescopes might experience a slightly increased rate of microscopic dust impacts, but we're talking about particles smaller than a grain of sand. It would be a minor annoyance for engineers, not a disaster. There could also be minor interactions with the solar wind. Charged dust particles can affect the local plasma environment, creating small, temporary perturbations in the magnetic fields and particle flows near the Sun. Scientists studying solar physics and space weather might notice interesting blips in their data, but again, nothing that threatens Earth directly or would be noticeable to anyone on the ground. Observationally, if 3I Atlas did break up, we should be able to see clear evidence over the coming weeks and months. The tail morphology should continue to evolve in complex ways as fragments separate and create distinct overlapping plumes. High-resolution imaging, especially from space-based telescopes like Hubble and James Webb, might resolve multiple nuclei, distinct bright spots where individual fragments are most active. The overall brightness might gradually decline as the fragments move away from the Sun and their activity drops, and the dust trails should become more elongated and diffuse. The timeline is important. The closest Earth approach on December 19th gives astronomers a golden, once-in-a-lifetime opportunity. The object will be relatively nearby, cosmically speaking, which means better angular resolution and the potential for more detailed images than we have ever obtained of an interstellar object. If there are fragments, if there are multiple pieces, that is when we are most likely to see them clearly. Telescopes around the world and in space are already gearing up for that date, scheduling precious observation time and preparing their most sensitive instruments. It is like the entire scientific community is waiting for a jury to deliver its verdict. Scenario A, the violent breakup, is the safest interpretation scientifically. It requires no new physics, no exotic explanations. It's just a comet, albeit an interstellar one, under immense stress doing what comets sometimes do. It's parsimonious, as scientists like to say, meaning it explains the observations with the fewest and most reasonable assumptions. But parsimony doesn't guarantee truth. Sometimes the simplest explanation is still wrong. Sometimes reality is weirder, more profound than the safe bet. So what if 3I Atlas didn't break up? What if it's still intact, a single coherent body, and all that activity, all those jets, all that impossible energy is coming from something else? That is scenario B, and that is where things get deeply, fundamentally unsettling. Let's now give the universe the chance to surprise us. Let's consider the alternative, the scenario that makes scientists uncomfortable but, given the data, cannot be dismissed entirely. What if 3I Atlas did not fragment? What if the nucleus is still intact, holding together as a single, solid unit despite the hellish conditions near the Sun and the jets, the color shifts, the non-gravitational acceleration are all being produced by something other than passive sun-driven sublimation? What if we are looking at propulsion? The clues for this are already there, embedded in the data, waiting for this interpretation. The non-gravitational acceleration means the object's trajectory is being altered by forces other than gravity. For a comet, that's usually explained by the rocket effect. Gas sublimating from the surface shoots off in one direction, pushing the nucleus in the opposite direction. That's normal. But the magnitude and the precise pattern of 3I Atlas's acceleration don't fit the typical profile. The nudges are too strong, too coordinated. They don't look like the random, chaotic pushes from natural outgassing. They look more deliberate, as if something is steering, making tiny corrections. Then there's the color shift, the fact that the object turned bluer than the sun. Typical comet activity doesn't do that. Sublimation produces visible and ultraviolet light from excited gas molecules, but not in a way that systematically shifts the overall color of the object bluer than the solar spectrum. You'd need either a very unusual chemical composition that we've never encountered, or an additional internal energy source, something heating or exciting the material far beyond what sunlight alone can do. It's the difference between a rock glowing from being in a fire and a light bulb emitting its own light. The energy budget problem is the big one, the most difficult to explain away. To produce jets as powerful and as sustained as those observed, you need an exhaust velocity much higher than the thermal speeds of simple sublimating gas. Sublimation gives you velocities on the order of a few hundred meters per second at most. The jets from 3I Atlas are clocked at around 400 ms, which is already at the high end. But to explain the observed thrust, the non-gravitational acceleration that's nudging its path, you'd ideally want exhaust velocities in the range of 3 to 50 kilometers per second. That's not sublimation anymore. That's not a dirty snowball melting. That's propulsion territory. That's the range of ion thrusters used on modern spacecraft or chemical rockets. That is the signature of material being actively, forcefully accelerated. Not just gently boiling off. Avi Loeb put it bluntly in one of his blog posts. Houston, we have a problem. The implication is clear. If 3I Atlas is intact, if the jets are coming from a single, coherent body rather than multiple fragments, then the energy required to produce them exceeds what solar heating can provide through standard comet processes. You need another source of energy. You need a power source. You need, in essence, engines. What would a surviving, actively propelled interstellar craft look like? It's a staggering thought to entertain. Imagine a probe, a vessel designed for the unimaginable durations and distances of travel between stars. It would be equipped with systems to adjust its trajectory, to deploy smaller sensor units, to study the environments it passes through. As it approaches a star, it might activate its propulsion systems to correct its course for a better flyby, using stored energy from its journey, or perhaps harvesting solar radiation with vast, invisible panels. The jets we see could be the exhaust plumes from those very systems, directed, controlled bursts of ionized gas or plasma. The color shifts could be thermal signatures from the engine cycling on and off, different parts of the structure heating and cooling. The changing tail morphology could be the result of different thrusters firing at different times, in different directions, creating a complex, evolving structure that looks chaotic to us but might be perfectly logical from an engineering perspective. This is speculation. Absolutely. There is no smoking gun here, no radio signal, no clear artifact like a metallic hull, no definitive proof. But the possibility exists, and it exists in the space between what we observe and what natural physics comfortably explains. It lives in the gaps. If 3I Atlas is artificial, if it's technology, then we are not just studying a comet. We are studying someone else's engineering, someone else's design, someone else's decision to send something into our system. We are, for the first time, not alone. What would you watch for if you suspected artificial origins? The checklist is both simple and profound. First, an intact nucleus. If high-resolution imaging on December 19th shows a single, coherent body rather than multiple fragments, that immediately rules out the natural breakup scenario and forces you to explain the immense activity some other way. Second, coordinated jets. If the plumes are firing in non-random patterns, if they are directional and timed in a way that suggests control rather than random outgassing from a rotating body, that's a major red flag. Third, subtle maneuvers. If the trajectory shows small, deliberate changes in velocity that don't match the expected profile of sublimation-induced rocket effects, that's highly suggestive. You'd also look for repeated patterns. Does the object brighten and dim in regular, complex cycles? Does the color shift repeat in a sequence? Does the activity surge correspond to specific distances or alignments with planets? Natural processes can produce periodicities, like a rotating nucleus exposing different areas to sunlight. But artificial systems might have different signatures, different rhythms, a kind of technological fingerprint. You'd want to rule out everything natural, every conceivable stretch of physics. before claiming anything artificial. But you'd keep your instruments ready, your data pipelines open, just in case. Then there's the ultimate question, communication. If this were a probe, would it be transmitting? Would it be listening? Efforts to search for radio or optical signals from 3i Atlas have so far turned up nothing but silence. But the absence of evidence is not evidence of absence. Maybe it's dormant, a derelict on a long automated journey. Maybe it uses frequencies or data modulations we're not monitoring or cannot yet decode. Maybe it's designed to be silent, a stealthy observer. Or maybe, and this is the most likely from a scientific standpoint, it's just a rock, and we're seeing patterns in the noise because our human brains are wired to find agency and intention where none exists. We are pattern recognition machines, and sometimes we recognize patterns that aren't there. The philosophical stakes here are enormous. If 3i Atlas is technology, if it's artificial, then we're not alone. And we've just had our first confirmed physical contact with something built by intelligence from another world. That changes everything. It changes how we see ourselves, our place in the galaxy, our future. It raises urgent, terrifying, and thrilling questions about intention. Why is it here? Is it observing us? Is it just passing through by chance? Or was its trajectory designed to bring it here? And if it was designed, what does that say about the civilization that designed it? Their capabilities, their motives, their age? Even entertaining this possibility feels dangerous, like crossing a line between rigorous science and wild science fiction. But science has crossed that line before and found reality on the other side. When quasars were discovered, some scientists briefly considered the possibility they were artificial beacons built by advanced civilizations. They weren't, but the question was worth asking. When pulsars were discovered, the regular radio pulses were so precise that astronomers jokingly called the first one LGM-1 for little green men. It turned out to be a neutron star, a natural explanation, but the speculation was legitimate given the data. 3i Atlas might be the same, a weird comet, nothing more. But the data is strange enough, the anomalies stacked high enough, that the artificial hypothesis cannot be dismissed out of hand. Not yet. Not until we have better images, better spectra, better trajectories. Not until December 19th, when the object makes its closest approach and we get our best look, our best chance to know. So here is where we stand. Scenario A says fragmentation, natural processes, a comet doing comet things under extreme conditions. Scenario B says intact, artificial, something that looks less like physics and more like engineering. Both are on the table, both have supporting evidence, both have gaps and problems, and the truth, whatever it is, will reshape how we think about interstellar visitors, about the galaxy, about whether we are alone. But 3i Atlas isn't the only strange thing happening in the cosmos right now. To fully understand its context, we need to look even deeper at its very substance. We need to drill down into its alien chemistry. Now we drill down into the chemistry because the composition of 3i Atlas is just as strange as its behavior, perhaps even stranger. While the jets and the acceleration capture the imagination, the silent language of its light spectrum tells a story that is equally revolutionary. When the James Webb Space Telescope pointed its powerful infrared instruments at the comet's coma, the spectra that came back were unlike anything ever recorded from a typical solar system comet. The carbon dioxide to water ratio, as we've discussed, was a shocking 8.1, but the deeper you look, the weirder it gets. SphereX, another space-based observatory, confirmed the findings and added more disturbing detail. The coma was incredibly bright in carbon dioxide emission, glowing intensely in the specific infrared wavelengths, where carbon dioxide molecules radiate after being excited by sunlight. Water and carbon monoxide, the other common volatiles in comets, were barely detectable ghosts in the data. The production rates for water and carbon monoxide were orders of magnitude lower than the carbon dioxide rate. It's as if this object is made primarily of dry ice, with just a trace of water frost, a fundamentally different kind of icy body. Polarimetry, a sophisticated technique that measures how light is polarized after reflecting off or scattering through a material, added another layer of profound mystery. 3i Atlas showed a deep negative polarization branch, hitting -2.7% at a specific phase angle. For non-experts, that's a precise measure of how much the reflected light's electric field is aligned in a particular direction after interacting with the comet's dust and gas. Negative polarization branches are rare and usually indicate very specific grain sizes and compositions. The value measured for 3I Atlas is unprecedented among all known comets and asteroids in our solar system. It doesn't match anything in our entire catalogue. The very way it scatters light is alien. So what does all this mean? The high carbon dioxide abundance suggests 3I Atlas formed in a region of its parent protoplanetary disk, where carbon dioxide ice was more stable and abundant than water ice. In our solar system, that's difficult to achieve. The outer regions beyond Neptune are cold enough for carbon dioxide to exist, but water ice is still far more abundant. For carbon dioxide to dominate so completely, you'd need an even colder environment, or one with a different initial chemical mix, a disk that was enriched in carbon and oxygen, but perhaps depleted in hydrogen. That points to a formation region far from its host star, or, more likely, around a star that itself had a different chemical composition than our Sun. This object is a refugee from a fundamentally different kind of planetary system. There's also the compelling cosmic ray hypothesis. Over millions or even billions of years of lonely interstellar travel, an object like 3I Atlas would be continuously bombarded by galactic cosmic rays, high-energy particles, mostly protons and atomic nuclei that permeate the galaxy. These particles can penetrate several meters into ice and rock, breaking chemical bonds, creating new molecules, and fundamentally altering the surface composition. One proposed mechanism is that cosmic rays convert carbon monoxide, which is common in interstellar ices, into carbon dioxide through a process called radiolysis, a radiation-driven chemical reaction. Over immense spans of time, the outer layers of the object, its skin, would become heavily enriched in carbon dioxide and complex organic molecules, creating a crust that is chemically distinct from the pristine interior. This cosmic ray processing hypothesis is very attractive to scientists because it explains not just the high carbon dioxide, but also the unusual polarization signature. The crust would be made of complex, carbon-rich grains and tholins, organic materials that scatter light in unique ways, different from the clean ice or silicate dust of fresh solar system comets. When those processed grains are ejected as part of the coma, they produce the bizarre polarization signature we observe. It's a self-consistent natural story, one that ties the object's strange composition directly to its long, irradiated journey through the emptiness between stars. But this also raises profound questions about its origin. Every interstellar object has a home, a star system where it formed, a planetary disk where it condensed out of gas and dust billions of years ago. Based on its incoming trajectory, astronomers can work backwards and estimate the rough direction from which 3I Atlas came. The results are intriguing. It didn't come from the direction of any nearby familiar star system like Alpha Centauri. Its path suggests it originated from the general direction of the galactic center, or perhaps from a region of active star formation hundreds of light years away. Pinpointing a specific source star is nearly impossible, but the implication is clear. This object has been wandering, a cosmic nomad, for a very, very long time. Perhaps since the early, more chaotic epochs of our galaxy, when star formation was more vigorous and planetary systems were frequently disrupted, ejecting their raw materials into the void. The composition also tells us something vital about the diversity of planetary systems in our galaxy. If 3I Atlas formed around another star, its bizarre chemistry reflects the conditions in that system. The carbon dioxide dominance suggests a colder, carbon-rich disk, maybe one that formed from a molecular cloud with higher metallicity or different isotopic ratios than the cloud that gave birth to our Sun. Every measurement we make of its gases and dust is a precious data point about how planets and comets form elsewhere, expanding our sample size beyond the single example we have in our own solar system. It is a glimpse into alien geology, alien mineralogy, alien ice physics. There's also the pressing population question. If 3I Atlas is representative of a common class of interstellar objects, radiation-processed bodies with organic rich crusts and high carbon dioxide content, then there could be many more like it passing through the solar system undetected at this very moment. Most would be too faint, too small, or too far away to spot, especially if they don't brighten significantly as they approach the Sun. Our current detection methods are heavily biased toward large, active objects like this one. We are likely missing a vast population of small, dark, inactive interstellar visitors. 3I Atlas might be the tip of an enormous iceberg, the one bright, obvious example in a hidden population of thousands or even millions that remain invisible to our telescopes. That has stunning implications for how we think about interstellar material exchange in the galaxy. Stars don't exist in isolation. They are born in clusters. They migrate through the galactic disk, and they gravitationally perturb each other's Oort clouds. Over billions of years, countless objects get ejected from one system and captured by another, or simply drift through interstellar space, carrying with them the chemical fingerprints of their origins. The galaxy is constantly shuffling its deck, mixing materials, exchanging the very building blocks of planets and perhaps life. 3I Atlas is part of that grand, cosmic process, a messenger from somewhere else, carrying information encoded in its atoms across the light years. This alien composition also, inevitably, tilts the puzzle toward the more exotic interpretations. If this object is so chemically different from anything we know, if its crust has been processed by cosmic rays into a layer of complex organic materials we don't fully understand, then maybe its behavior near the sun is equally alien. Maybe the physics governing how it sublimates, how it releases gas, how it responds to solar heating is fundamentally different from the physics we've derived from studying our own comets. Maybe we are mistakenly applying models built for solar system comets to something that doesn't play by those rules. Or, and this is where the speculation gets uncomfortable again, maybe the composition is deliberate. If you were building an interstellar probe designed to last for eons, you would want materials that could survive the harsh environment of empty space. You'd want a crust that could act as a shield against cosmic rays, that could self-repair, or at least remain stable under constant radiation bombardment. You'd want volatiles that could be used as propellant, stored in stable ices that could be made to sublimate predictably when nearing a star. A carbon dioxide-rich composition fits that bill remarkably well. It's dense, it sublimates cleanly, it's relatively easy to handle chemically. A carbon dioxide-dominated object might not be a natural accident. It might be an engineered design feature. That is a stretch, absolutely. There is not a shred of direct evidence that the composition is artificial. But once you start seeing persistent anomalies in one area, the behavior, it becomes harder to ignore the anomalies in another area, the chemistry. They reinforce each other, building a circumstantial case that something about 3I Atlas is fundamentally different from our expectations. The cosmic ray processing idea is the best natural explanation for the composition, and it's a very good one. It fits the data, it's supported by known physics, and it's testable in principle. If we could somehow sample the surface directly, if we could analyze that organic crust in a laboratory, we could likely confirm or refute it. But we can't. We are stuck observing from millions of kilometers away, inferring chemistry from the faint whispers of photons, building models from spectra. It's detective work of the highest order, but with incomplete clues, and the jury is still out. What is clear is that 3I Atlas is chemically alien. Whether that alien nature is the result of natural processes in a different stellar environment, or radiation exposure over eons, or something more deliberate, we don't yet know. But the composition matters because it directly shapes how the object behaves, how it responds to the sun, and ultimately, the answer to our central question: did it break apart, or did it survive? To understand what might have happened, we need to delve into the brutal physics of a breakup. The phrase breaking apart sounds simple, but the mechanics are anything but. A comet isn't a solid monolithic rock. It's a rubble pile, a loosely bound collection of smaller chunks, pebbles and boulders, all held together by the faintest of gravitational forces and the weak structural strength of ice acting as a glue. The tensile strength, the force required to pull it apart, is incredibly low. You don't need a planet-sized sledgehammer to destroy it. You just need the right kind of stress, in the right places, at the right time. Solar heating is the primary culprit, the trigger for the catastrophe. As 3I Atlas fell toward the sun, the surface temperature on its sunward side skyrocketed. Ice, particularly the volatile carbon dioxide, began sublimating rapidly, turning directly from solid to gas. But this process is never uniform. Some areas of the nucleus might be darker, absorbing more heat. Others might be covered in a layer of dust that insulates the ice beneath. The result is differential heating, hot spots and cold spots existing side by side, creating severe thermal gradients that generate immense internal stress. Ice expands and contracts with temperature changes, and if those changes are rapid and uneven, cracks form, spread, and merge deep within the body. Then there's the internal gas pressure. As volatiles sublimate not just on the surface, but beneath it, The resulting gas can become trapped under layers of non-volatile dust and crust. The pressure builds, like a pot coming to a boil with a lid on. Eventually the lid blows, the crust ruptures, and the trapped gas explodes outward in a violent outburst, carrying dust and fragments with it. This is what causes the sudden, dramatic brightenings sometimes seen in solar system comets. If enough of these pressurized pockets build up simultaneously, and if the overall structure is weak enough, the entire nucleus can shatter like a glass ball under pressure. Tidal forces add another layer of stress. The sun's gravity pulls harder on the near side of the comet than the far side, creating a stretching effect, a subtle but persistent pull to tear it apart. For a large object passing very close to a massive body, this tidal gradient can be immense. That's what tore Shoemaker-Levy 9 apart near Jupiter. 3I Atlas passed perihelion at a distance of about 1.35 astronomical units, which is actually farther than Earth's orbit. So the tidal forces from the sun at that distance aren't as extreme as they would be closer in. But when combined with the intense internal stresses from uneven heating and building gas pressure, even modest tidal forces could provide the final nudge needed to push the object over the edge from cracking to catastrophic fragmentation. Rotation also plays a critical role. If the nucleus is spinning, centrifugal force pushes outward, adding yet another source of stress. Comets can spin quite fast, sometimes with periods of just a few hours. If 3I Atlas was already rotating rapidly and then began outgassing asymmetrically, with jets acting on one side more than the other, those jets could act like tiny, misaligned rocket engines, spinning the nucleus even faster, or chaotically changing its rotation axis. This spin-up effect adds more mechanical stress, making a breakup more likely. It's a feedback loop of destruction. Outgassing causes rotation, which causes stress, which causes more fracturing and outgassing. If fragmentation did occur, the pieces would initially stay relatively close together, perhaps just a few kilometers apart, but immediately they would begin to drift, moving at slightly different velocities due to their different masses and the varying thrust from their individual outgassing patterns. Over hours and days, the fragments would spread out along the orbit, creating a linear structure, a train of icy debris. Over weeks and months, that train would stretch, eventually spanning millions of kilometers. A long, faint string of icy pearls slowly diverging on their way out of the solar system. Avi Loeb's estimate of at least 16 fragments comes from this kind of calculation, matching the observed activity level to the required surface area. If the original nucleus was 5.6 kilometers across, its surface area was roughly 98 square kilometers. To get 16 times more area, you'd need either 16 similarly sized pieces or a cloud of many smaller ones. The exact number depends on the violence and style of the breakup, whether it was a relatively clean split into large chunks or a chaotic, explosive shattering into a cloud of gravel and dust. Each fragment would then behave like its own mini-comet. It would have its own tiny coma, its own jets, its own unique outgassing pattern. From our vast distance, the combined glow of all these fragments might look like a single, large and fuzzy blob, rather than distinct points of light. This could explain why observers haven't definitively resolved multiple nuclei yet. The fragments might be too close together for our telescopes to separate, or too faint individually, their light drowned out by the overwhelming brightness of the combined giant coma they produce. The debris field would be more than just the fragments. It would include a vast amount of dust. Fragmentation exposes fresh, pristine ice from the interior, which then sublimes more aggressively, ejecting more dust grains. This dust spreads out under the gentle but constant pressure of sunlight, forming a broad, fan-shaped cloud along the orbit. The particles would range in size from sub-micron specks to millimeter-sized pebbles. The smallest ones are pushed away from the sun most strongly, creating a wide fan, while the larger, heavier ones follow paths closer to the original orbit of the parent body. What does this mean for us? Practically, very little, and that's reassuring. Earth's orbit is nowhere near the trajectory of 3I Atlas, so our planet will not pass through this debris field. There is no risk of a meteor storm. However, other spacecraft might, satellites in high Earth orbit, or interplanetary probes, or solar observatories could potentially encounter a few stray dust particles from the cloud. The risk is minimal, space is big, and the cloud is diffuse, but it's not zero. A single tiny grain of silicate or ice hitting a sensitive instrument at a relative velocity of tens of kilometers per second could cause pitting or electrical damage. Mission planners are aware of this and are tracking the comet's predicted debris distribution, but it's considered a very minor concern, not a mission-ending threat. There's also the interaction with the solar wind. Dust particles in space quickly pick up an electric charge from ultraviolet light and collisions with solar plasma. This charged dust can then interact with the solar wind, the stream of charged particles flowing from the sun. In a dense dust cloud, this interaction can create local, temporary disturbances in the magnetic field, tiny ripples in the flow. Scientists studying space weather with instruments on satellites might see interesting minor anomalies in their data, little blips and dips that correspond to the comet's passage and its extended debris field. It would be a curious footnote in the data, not a global event. Visually, from Earth, even a fragmented three-eye atlas might not look dramatically different to the casual observer. The comet is already faint, requiring decent telescopes to see. If it broke into many pieces, each piece might be even fainter and harder to track individually. But the combined glow could create fascinating effects for astrophotographers. A stretched-out, patchy tail, or multiple tail structures seeming to emanate from a blurred, elongated core. Amateur astronomers with backyard telescopes have been monitoring three-eye atlas closely, and some have already reported seeing hints of complexity in the tail, subtle irregularities that could be the first visual evidence of underlying fragmentation. The timeline for observation is now everything. December 19th, 2025 is the date. That is when three-eye atlas makes its closest approach to Earth, about 0.6 astronomical units away, or roughly 90 million kilometers. That is the best opportunity we will ever have for high-resolution imaging, for detailed spectroscopy, for truly characterizing this visitor. If fragments exist, that is when we will see them most clearly. If the nucleus is miraculously still intact, that is when we will be able to measure its size and shape most accurately. Telescopes worldwide, from professional observatories to advanced amateur setups, are coordinating observation campaigns for this brief window. It's a period of just a few days when the geometry is optimal, and then the comet will continue its journey outward, fading into the distance, carrying its secrets with it if we fail to grasp them now. What if the fragmentation hypothesis is wrong? What if the observations on December 19th reveal with stunning clarity a single, intact nucleus with no sign of breakup? Then we are thrust back into scenario B, back to the unsettling and thrilling possibility that the activity, the jets, the energy are coming from something other than natural sublimation from a shattered body. That brings us back to the artificial hypothesis, the speculation that refuses to go away. But before we can fully embrace that line of thinking, we must step back from the pure science and look at the human drama surrounding this object. Because this story isn't just about a comet. It's about how science operates under the spotlight, how battles over data and credibility are fought, and how the world reacts when faced with the truly unknown. Let's say it out loud. Let's give voice to the elephant in the room. The artificial hypothesis, the idea that three-eye atlas might be technology, a probe, an artifact, something built by an intelligence from another world. It is the possibility that lurks beneath every anomaly, every unexplained data point. Every time a scientist says, "That's odd," and while mainstream astronomers are careful, cautious, and rightly reluctant to speculate without ironclad evidence, the speculation is happening anyway. It's happening in the comments of blog posts, in the preprint papers that bypass slow journal review, in hushed conversations at conferences, and most of all, in the wide expanse of the public imagination. Avi Loeb has been the most prominent and vocal scientist suggesting we should not, and cannot, rule out artificial origins. It's important to understand who he is. He is no fringe figure. He is a tenured professor at Harvard University, the former chair of its astronomy department, a respected theorist with hundreds of peer-reviewed papers to his name. He is also a scholar who is willing to ask uncomfortable questions, to push against the scientific consensus when he believes the data warrants it. His involvement with Oumuamua, where he famously suggested it might be a light sail, a piece of alien technology, made him a controversial figure. Some colleagues praised his intellectual courage and willingness to think outside the box. Others criticized him fiercely for going too far, for speculation that they felt crossed the line into sensationalism and harmed the credibility of the field. With three-eye atlas, Loeb is asking the same kind of provocative, boundary-pushing questions. In his detailed blog posts, he has laid out the evidence like a prosecutor building a case. The carbon dioxide dominance that doesn't fit any comet model, the energy budget problem, where the required surface area vastly exceeds the observed size, the non-gravitational acceleration that suggests coordinated thrust rather than passive, chaotic outgassing, the strange color shifts that hint at an additional internal energy source, and the statistical oddity. Why is an object this large, this strange? One of the first 3 interstellar visitors we ever see. Each piece of evidence individually might be explained away, but together, he argues, they form a pattern that resists easy categorization into comet. He has also pointed out intriguing orbital characteristics. 3I Atlas came into the solar system on a retrograde orbit, meaning it's moving in the opposite direction to the general flow of planets and most other bodies. This isn't impossible for a natural interstellar object, but it is less common. Its orbit is also roughly aligned with the ecliptic plane, the flat disk where most planets orbit. Again, not impossible, but statistically less likely for a truly random interloper from the galaxy. If you were designing a probe to efficiently survey a solar system, you might very well choose a trajectory that takes you through the ecliptic plane, where the majority of the interesting stuff, planets, asteroids, comets, is located. It's the busiest highway in the system. Then there's the language Loeb uses, language that deliberately evokes engineering. He suggests that jets with exhaust velocities potentially in the 3 to 50 kilometers range look less like sublimation and more like propulsion. Ion thrusters, like those used on NASA's Dawn spacecraft or Deep Space One, produce exhaust speeds in that exact range by using electric fields to accelerate ions. Chemical rockets can do even better. If 3I Atlas has jets operating at those velocities, and if the nucleus is intact, then you need an explanation for where the energy is coming from. Solar heating alone cannot account for it. The phrase, "Houston, we have a problem," isn't just dramatic flair. It's Loeb's way of stating that the conventional models are breaking down, that something fundamental doesn't add up, and that we need to seriously, rigorously consider alternatives. Those alternatives include exotic natural processes we haven't discovered yet, but they also, necessarily, include the possibility of technology. What would constitute strong, convincing proof? That is the million-dollar question. Speculation is easy. Proof is hard. If you wanted to definitively show that 3I Atlas is artificial, what would you look for? A clear, unambiguous radio signal would be the smoking gun, a deliberate, narrowband transmission that carries information or a pattern that cannot be explained by any known natural emission, like a plasma oscillation or stellar pulsation. Scientists have already used radio telescopes to listen to 3I Atlas. So far, they have heard nothing but the usual silence of space. But the absence of a signal is not proof it's not there. Maybe it's not transmitting. Maybe it uses a frequency or a data modulation we are not monitoring. Maybe it only transmits at specific times or when triggered. Optical signals would be another clue. Deliberate, patterned flashes, pulses of light that don't correlate with rotation or outgassing. So far, the brightness changes seem messy and consistent with a lumpy, rotating, active nucleus. But subtle, repeating patterns might be buried in the noise, waiting for more sophisticated analysis to uncover. Trajectory maneuvers would be perhaps the most compelling evidence of all. If the object made a clear, deliberate course correction, a change in velocity that cannot be explained by gravitational interactions with planets or by the rocket effect of asymmetric outgassing, that would be very, very difficult to explain naturally. Monitoring its orbit with extreme precision over the coming months and years will be critical. Even small anomalous deviations from the predicted path could be highly significant. Then, there's the ultimate, unnerving question of intent. If this is a probe, why is it here? Is it a simple observer, silently mapping our solar system, collecting data on the planets and the strange, noisy species on the third one? Is it merely passing through by sheer cosmic chance, a derelict from some ancient, long-forgotten mission, now drifting aimlessly through the galaxy? Or is it something else entirely? A piece of interstellar infrastructure, a navigation buoy, a warning marker, or even a weapon? The possibilities, both wondrous and terrifying, multiply exponentially once you admit the hypothesis into serious consideration. The public fascination with this angle is undeniable and has become a powerful force in the story. Celebrities have weighed in, amplifying the signal to hundreds of millions of people. Kim Kardashian posted about 3i Atlas on social media, asking her followers if it was finally the aliens. Joe Rogan discussed it at length on his immensely popular podcast, inviting speculation from guests and his massive audience. Coverage has appeared everywhere, from the light-hearted pages of People magazine, to the provocative headlines of the New York Post, to the more measured, but still intrigued, pages of scientific publications like New Scientist and Science. The hype is real, and it's a double-edged sword. On one hand, this massive public interest drives funding, encourages telescope time to be allocated, and brings welcome attention to the fields of astronomy and planetary science. On the other hand, it creates immense pressure for sensational conclusions, rewards speculation over slow, careful rigor, and can poison the well of sober scientific discourse. Scientists are caught in the middle of this media storm. They need to maintain their hard-won credibility, which means being painstakingly careful, conservative, and not making claims they cannot back up with overwhelming evidence. But they also need to be intellectually honest about the uncertainty, about the fact that 3i Atlas simply does not fit neatly into existing categories. Saying we don't know is scientifically the most accurate statement, but it is not satisfying to a public hungry for answers, and it leaves a vacuum that others are all too happy to fill with wilder, less disciplined ideas. The risk of speculating too freely is that you lose your scientific credibility if you're wrong. Loeb has experienced this firsthand. His Oumuamua light sail hypothesis drew intense criticism, and while some of it was legitimate scientific disagreement, some of it was personal, attacking his motives and his competence. He has developed a thick skin, but the dynamic can be toxic for science as a whole. Science works best when people can propose radical ideas without fear of career-ending reprisal. But it also needs robust mechanisms, like peer review, to filter out nonsense, to distinguish bold speculation from evidence-backed claims. The reward, though, if the artificial hypothesis turned out to be true, would be incalculable, beyond anything in human history. The confirmation of extraterrestrial technology, even a silent, derelict probe, would be the most significant discovery ever made. It would prove we are not the only intelligence to have arisen. It would show that technological civilizations can and do exist, or have existed, beyond Earth. It would reshape philosophy, religion, culture, politics, and our very conception of reality. It would give us a benchmark, a comparison point, a terrifying and glorious glimpse into what is possible for a civilization that reaches for the stars. It would be the definitive end of one era of human history and the beginning of another. But we are not there yet. We are in the messy, frustrating, and exhilarating middle. The data is ambiguous, the interpretations are hotly contested, and the truth remains unknowable until we get better observations. December 19th is coming. The telescopes are being pointed. The questions are being sharpened. And whatever we learn, whether 3i Atlas is a broken comet or something far stranger, the answers will matter forever. For now, the technology speculation remains just that, informed speculation. But it is speculation driven by real persistent anomalies, by real data that steadfastly challenges our models. And that alone makes it worth our attention, even if it makes us profoundly uncomfortable. The next part of this story isn't about the object itself. It's about us, the humans trying to understand it, and the battles over who gets to see the data and how transparent we should be when facing the truly extraordinary. Science likes to present itself as a purely objective, transparent endeavor, driven solely by evidence and reason. And at its best, it is. But science is also done by humans, funded by institutions, and subject to the messy realities of politics, egos, and intense competition. When something as profoundly strange as 3i Atlas appears, these human factors come to the forefront, and the battle over data access and interpretation becomes almost as fascinating as the object itself. Here is the situation. Multiple world-class observatories have been studying 3i Atlas since its discovery. Ground-based telescopes in Chile, Hawaii, Arizona, and elsewhere have been tracking it, taking thousands of images, measuring its brightness and spectrum. Space-based instruments like the Hubble Space Telescope, the James Webb Space Telescope, and the SphereX mission have contributed priceless infrared and ultraviolet data, piercing through the glare to see its chemistry. And a global network of dedicated amateur astronomers has added their own observations, filling in the temporal gaps and providing continuous coverage that the oversubscribed professional telescopes can't match. But not all of this data is publicly available. Not yet. A significant portion is proprietary, held by the research teams who were awarded the precious observing time, giving them exclusive access for a limited period, typically 6 to 12 months, to analyze the data and publish their findings. This is standard, long-standing practice in astronomy. Observing time on major telescopes is a fiercely competitive resource. The teams that win that time, through rigorous proposal processes, get the first right to mine the data for discoveries. The idea is to reward the immense effort and expertise that goes into making these complex observations, to give the researchers a window to do careful, thorough analysis before releasing raw data that others might misinterpret, or worse, use to scoop their original work. The problem arises when the object in question is so unusual, so potentially momentous, that the global public interest vastly exceeds the pace of the normal scientific process. People want answers now. They want to see the raw Hubble images, read the James Webb spectra, and evaluate the evidence for themselves. And when data is held back, even for these legitimate and traditional reasons, suspicion grows. Is something being hidden? Are scientists or government agencies covering up evidence? Is there a conspiracy to suppress the truth about an alien visitor? This suspicion reached a fever pitch recently when a US lawmaker, responding to constituent pressure and the public fascination, formally requested that NASA release any high-resolution images of 3I Atlas taken by the HiRISE camera on the Mars Reconnaissance Orbiter. Wait, you might say, HiRISE is designed to photograph the surface of Mars from orbit, not to track distant comets. This is true, but the camera has exceptional resolution, capable of seeing objects the size of a kitchen table on the Martian surface. If it could be pointed at 3I Atlas during a favorable alignment, the thinking went, it could potentially resolve surface features or multiple nuclei in stunning detail that other telescopes cannot. The request was denied. Officially, the reason was that HiRISE wasn't designed or tasked for that kind of observation, and reallocating its resources would disrupt planned and critical Mars science. But the denial, however justified, inevitably fueled further speculation in online forums that NASA has images showing something extraordinary and is deliberately withholding them. There is no credible evidence for this conspiracy theory. HiRISE almost certainly has not imaged 3I Atlas, and even if it had, the vast distance and the object's faintness would make resolving any fine details nearly impossible. But the incident perfectly illustrates the growing tension between the slow, methodical scientific process and the public's intense demand for immediate transparency. When you're dealing with something that could potentially be the first confirmed piece of extraterrestrial technology, the usual rules and timelines feel agonizingly slow, even inadequate. Peer review is another flashpoint in this story. Many of the initial findings about 3I Atlas have appeared not in formal peer-reviewed journals, but in preprints, papers posted on servers like archive.org before they have undergone formal peer review. Avi Loeb's influential Medium blog posts are even less formal, more akin to public commentary and real-time scientific brainstorming than to formal publication. This is not inherently a bad thing. Preprints allow for the rapid dissemination of results, allowing the global scientific community to react and respond quickly. Blog posts can communicate complex ideas and intriguing possibilities to a much broader audience, but they also bypass the essential quality control that peer review provides. Mistakes can be made and can propagate quickly. Exciting speculation can be presented with the authority of a Harvard professor and be misinterpreted as established fact. Readers without deep expertise may struggle to distinguish between a credible, data-based analysis and an intriguing but unproven fringe theory. The challenge is that the traditional peer review process is slow, often taking many months, sometimes over a year. For a fast-moving target like 3I Atlas, which is changing week by week and will soon be out of range, waiting for formal publication means potentially lagging forever behind the observations. By the time a peer-reviewed paper appears, the comet may have faded, making new observations impossible, or new data may have already rendered the analysis obsolete. So researchers are caught in a bind between the need for speed and the need for rigor, between open collaboration and protecting their work. Public trust in science is also on the line. The world is watching, reading the headlines, and forming opinions. If the scientific community seems evasive, if it withholds data behind paywalls, or speaks in jargon-heavy language that obscures more than it clarifies, public trust erodes. And when trust erodes, conspiracy theories flourish. They thrive in environments where official information is scarce, slow, or contradictory. And once that trust is lost, it is incredibly difficult to rebuild. The involvement of celebrities and influential media figures further complicates the narrative. When Kim Kardashian tweets about 3i Atlas to her hundreds of millions of followers, or when Joe Rogan devotes a long segment of his podcast to speculating about alien probes, the narrative escapes the control of the scientific community. These figures have a reach and influence that far surpasses that of any astronomer or science communicator. Their commentary, even if well-intentioned, can accidentally amplify misinformation, create unrealistic expectations, or trivialize profound scientific questions. Yet at the same time, this celebrity attention brings millions of eyes and minds to the topic. It raises public awareness of astronomy, of the search for extraterrestrial intelligence, of the sheer wonder and mystery that still exists in our universe. It can inspire a new generation of young people to look up at the sky, to ask big questions, to pursue careers in science. The trick, the nearly impossible balancing act, is to harness this enthusiasm while steadfastly adhering to accuracy, to ride the wave of hype without abandoning the anchor of humility and evidence. Open data advocates argue that much of this tension would be solved by radical transparency. If all observations of 3i Atlas were immediately released to the public, if every raw data file were freely available the moment it was downlinked, then a global army of independent analysts, amateur astronomers, and citizen scientists could contribute to the science. This has happened before with great success. Projects like Galaxy Zoo, where volunteers classified the shapes of millions of galaxies, led to discoveries that professional astronomers had missed. Citizen scientists have found exotic exoplanets, tracked potentially hazardous asteroids, and contributed to countless other research projects. The collective power of the crowd can be immense, but open data also has its risks. Not everyone has the expertise to interpret complex, raw astronomical datasets. Misinterpretations can spread like wildfire on social media, creating confusion and false narratives that are hard to correct. There's also the legitimate issue of credit and career incentives. If a team spends years developing a complex instrument, writing a detailed observing proposal, and painstakingly analyzing the data, only to have their Nobel Prize-worthy result scooped by someone who quickly analyzed the publicly released data, that feels deeply unfair and could discourage the very work that produces the data in the first place. The history of previous interstellar objects offers valuable lessons. When Oumuamua was discovered in 2017, the data were relatively open, and many teams across the globe published analyses. That openness led to vigorous, healthy debate, competing interpretations, and eventually a broad consensus that Oumuamua was probably a natural object, albeit a very unusual one. But it also led to persistent fringe claims, sensational headlines, and a lasting controversy, particularly around Loeb's light sail hypothesis. The second interstellar visitor, Tui Borisov, was more straightforward, behaving much like a standard comet, and the scientific response was consequently calmer and more measured. Atlas is shaping up to be far more like Oumuamua than Borisov, but amplified. The anomalies are too significant to ignore, the questions too big to dismiss. And that means the politics, the debates, the battles over data access and interpretation will continue to rage. What matters most now is that the observations continue, that the analysis is as rigorous as humanly possible, and that scientists communicate with honesty and clarity about what they know, what they don't know, and what the different possibilities are. If 3i Atlas turns out to be a broken comet, fine. We will have learned invaluable lessons about the strength and composition of interstellar objects. If it turns out to be something stranger, then the transparency and rigor with which the discovery is handled will determine whether it is remembered as a triumph of open, collaborative science or a cautionary tale of missed opportunities and public mistrust. For now, the data is still coming in. December 19th approaches, and the world is watching. But 3i Atlas isn't happening in a vacuum. To fully appreciate its significance, we need to zoom out from this single, strange object to the broader cosmic context. Why does this one visitor matter so much in the grand scheme of things? Take a step back, breathe, take the widest possible view. Since humans first started seriously studying the sky, since Galileo pointed his primitive telescope upward and saw the moons of Jupiter, since Edwin Hubble revealed that the fuzzy nebulae were actually entire galaxies far beyond our own, we have been on a relentless journey of discovery that has consistently shown us that the universe is bigger, older and infinitely stranger than we ever imagined. Every generation thinks it has the picture mostly figured out, and every generation is proven wonderfully, humblingly wrong by new observations. 3I Atlas is the latest and one of the most potent in a long line of such humbling discoveries. Consider the sheer statistical rarity. Only 3 interstellar objects have been confirmed entering our solar system in all of human history. 3. Oumuamua in 2017, cigar-shaped and tumbly, defying easy classification. 2 Borisov in 2019, more comet-like, more comfortable, but still an outsider. And now we have 3I Atlas, the largest and most anomalously active of the 3, pushing the boundaries of explanation to the absolute limit. Think about the environment these objects traverse. Interstellar space is vast, nearly empty. Stars are separated by light years of nothingness. Distances so immense that even traveling at a significant fraction of the speed of light would take decades or centuries to cross them. Objects that get ejected from one planetary system drift for millions of years before encountering another. The odds of detecting one passing through our relatively tiny patch of the sky during our brief blip of modern observational capability are astronomically low. And yet, we've now seen 3 in less than a decade. What does that tell us about the true population of interstellar objects? If we've detected 3 with our current, still improving surveys, how many are out there that we're missing? Estimates vary, but some models suggest there could be thousands of interstellar objects larger than 100 meters passing through the inner solar system at any given time. Most are too small, too dark, or too inactive for us to detect. The upcoming Vera C. Rubin Observatory, with its immense, rapid scanning capabilities, is expected to find dozens more each year. 3I Atlas might be the herald, the first loud announcement of a coming flood of interstellar visitors. And if they are this common, if the galaxy is constantly exchanging material between star systems, then our models of solar system formation and evolution need a fundamental update. We have long thought of our system as an isolated, self-contained unit, shaped only by its own internal processes and the occasional comet or asteroid from our own Oort cloud or Kuiper belt. But if interstellar visitors are frequent, if they bring chemicals and materials from other systems, then the mixing is ongoing. The solar system is not a closed box. It is part of a vast galactic ecosystem, constantly exchanging matter and information over deep time. That realization has philosophical weight. We are not isolated. We are not alone in a cosmic sense. Even if we haven't found intelligent life, the very molecules in 3I Atlas were forged in another stellar nursery, shaped by another star's light, processed by the same universal forces that shaped us. There is a continuity, a connection that spans the entire galaxy. And if raw material can travel between stars, if chemistry and geology are galactic processes, then maybe life can be too. The theory of panspermia, the idea that life's building blocks, or even simple life itself, might spread between worlds via comets and asteroids, becomes far more plausible. Maybe the seeds of life on Earth hitched a ride on an object like 3I Atlas billions of years ago. Maybe that's how life begins everywhere, as a galactic infection, a spark that jumps from one stellar system to another on the backs of icy wanderers. Atlas also matters for intensely practical reasons: planetary defense and future space exploration. If interstellar objects are common, if they can enter our system on unpredictable hyperbolic trajectories, then tracking them becomes a priority for our long-term survival. The vast majority pose no threat, but eventually, statistically, one might be on a collision course. Knowing how to detect them early, how to characterize their orbits quickly, and how to assess the risk they pose are no longer abstract exercises. They are essential skills for a spacefaring civilization, and if we are serious about sending our own probes to other stars, ambitious missions like Breakthrough Starshot that aim to accelerate tiny, laser-driven sails to a fraction of light speed, then understanding what's in the space between here and there is critical. Interstellar space isn't a perfect vacuum. There's dust, gas, radiation, and, as 3I Atlas shows, solid objects large enough to destroy a spacecraft on impact. This visitor gives us our first real data on the density, size, and composition of these hazards. It is a reconnaissance mission for our own future voyages. But the real deepest reason 3I Atlas matters is more existential. It forces us as a species to confront profound uncertainty. It makes us sit in the discomfort of not knowing. Is it a comet? Is it technology? Is it something we don't even have the words for yet? The answer matters, of course, but the process of asking, the collective willingness to entertain possibilities that challenge our entire worldview, is where real growth happens. That's where science transcends mere data collection and becomes a way of thinking, a way of being in the universe, open to surprise, humble in the face of evidence, and always ready to update our most cherished beliefs. If 3I Atlas is a broken comet, we've learned that interstellar bodies can fragment dramatically near a star, that carbon dioxide-dominated compositions exist in nature, and that cosmic ray processing can create complex organic crusts on objects that wander the galaxy. That is immensely valuable. It refines our models, gives us new data points, and expands our understanding of cosmic chemistry. If 3I Atlas is intact and doing something stranger, if there's even a small chance it's artificial, then the implications multiply exponentially. We are not alone, meaning consciousness and technology have arisen elsewhere, and we have just had our first, confirmed, physical brush with it. That changes everything. How we see ourselves, our place in the cosmos, what we prioritize as a civilization. It all gets rewritten. And even if we never get a definitive answer, even if 3I Atlas fades into the interstellar dark, leaving us with more questions than answers, the entire exercise has immense value. We have pushed our instruments and our minds to their limits. We have debated interpretations, refined our techniques, and collaborated across institutions and nations. We have engaged the global public, sparked imaginations, and reminded millions of people that the universe is still a place of wondrous, deep mystery. That is worth something. That is worth a great deal. The story of 3I Atlas is still unfolding. December 19th will bring new data, new clues. Months and years of follow-up observations will track its fading light, its unchanging or changing trajectory. Papers will be published, debated, and revised. A consensus might slowly emerge, or the controversy might deepen and harden. But whatever happens, this object has already left its mark on us. It has made us think harder, look closer, and question more deeply. And it's crucial to know that it's not alone in this. The universe has been serving up other profound surprises recently. Other discoveries that challenge our assumptions and expand our horizons in parallel. 3I Atlas is part of a broader pattern, a moment in time when our observational capabilities are leaping forward and the cosmos is revealing itself to be stranger than we predicted. While 3I Atlas has been occupying headlines and commanding telescope time, other quieter cosmic stories have been unfolding, stories that are fundamentally reshaping how we think about the universe's past, present, and ultimate future. One of the most significant comes from the Euclid mission, a European Space Agency telescope launched in 2023 to map the large-scale structure of the universe with unprecedented precision and to probe the mysterious nature of dark energy. Euclid's latest data release, which landed in 2025, contains a finding that many might have missed amid the comet excitement. The rate of star formation in the universe has peaked. It is now in a long, steady, and irreversible decline. The cosmos, in a very real sense, is cooling down. This might not sound immediately dramatic, but its implications are profound. For billions of years after the Big Bang, the universe was in a frenzy of creative activity. Massive clouds of primordial hydrogen and helium collapsed under gravity, igniting nuclear fusion and creating the first brilliant stars. Those first-generation stars lived fast, died young, and exploded as supernovae, enriching the cosmos with the heavier elements essential for life: carbon, oxygen, iron, and more. New generations of stars formed from this enriched material, creating planets, moons, and eventually the conditions for biology. Star formation was the great engine of cosmic evolution, the process that turned simple gas into complex structures. But this engine is not running at a constant rate. It peaked sometime around 10 billion years ago, during the universe's energetic middle age, when galaxies were closer together, colliding frequently, and triggering immense bursts of star formation in their spiral arms and dense cores. Since that golden age, the rate has been declining, slowly at first, but now more noticeably. Euclid's data confirms that fewer new stars are being born now than at any other point in the recent cosmic history. The universe is entering a quieter, more sedate phase, where existing stars will age and die, and fewer new ones will take their place. The era of cosmic construction is winding down. Why is this happening? Part of the reason is simple exhaustion. The raw fuel for star formation, cold hydrogen gas, is being used up, locked away in long-lived stars, or blown out of galaxies by supernova winds and active galactic nuclei. But another, more mysterious force is also at work: dark energy. As dark energy causes the expansion of the universe to accelerate, galaxies are being pushed apart from one another. These larger distances mean galactic collisions and close encounters, which are primary triggers for star formation, become much rarer. The universe is becoming a lonelier place, and the gravitational interactions that stir up gas clouds and cause them to collapse are diminishing. The implications are staggering to contemplate. Fewer new stars mean fewer new planetary systems. It means the future universe will be progressively darker, colder, and more dominated by the fading embers of old stars, white dwarfs, neutron stars, and black holes. It means that opportunities for new life to arise, at least life as we know it that depends on sun-like stars and planets, will become increasingly rare. We are living in a privileged era, a cosmic sweet spot where star formation is still robust enough to create Earth-like worlds, but that era is finite. Billions of years from now, the universe will be a much dimmer, more static, and far less hospitable place. How does this connect to 3I Atlas? On the surface, they seem entirely unrelated. One is a single specific object passing through our solar system. The other is a universal trend spanning billions of light years. But both powerfully challenge the deep-seated human assumption that the cosmos is in a steady state, that what we see now is what has always been and always will be. Just as 3I Atlas does not behave like a normal comet, the universe itself does not behave like a forever young, star-producing factory. Both are profound reminders that change is the only constant, that nothing in the cosmos is static, from the smallest comet to the largest scales of reality. There is also a poignant thematic link. If star formation is declining, if new planetary systems are becoming rarer, then the objects that already exist, the comets, the asteroids, the rogue planets, and potentially the artifacts of past civilizations, become increasingly important. They become the primary carriers of material and information between the aging star systems. The emphasis of the cosmos may be shifting from a phase of vibrant creation to a long, slow era of circulation and recycling. The wanderers, like 3I Atlas, may become the central characters in the galaxy's later chapters. It also shifts our perspective on detection. If interstellar visitors are relatively common now, they might become even more frequent in the far future, as older systems eject more of their leftover building blocks into the void. The galaxy could be entering an era where the dominant activity is the exchange of ancient materials between dying systems, rather than the birth of new ones. The Euclid findings and the story of 3I Atlas both underscore something fundamental about our place in cosmic history. We live in a universe that is approximately 13.8 billion years old, and we're observing it at a very specific moment in its multi-billion-year evolution. That moment happens to be after the peak of star formation, but before the universe has gone completely dark. We are in the cosmic twilight, watching the great engines begin to wind down, but not yet extinguished. And 3I Atlas is passing through during this same twilight, a visitor from a galaxy that itself has a history, an object that might be a remnant from its own system's peak era of activity, billions of years ago. There is a profound poignancy to that realization. The universe had its wild creative youth, its peak of productivity, and now it is settling into a long, gradual decline. Not a catastrophic collapse, not a dramatic ending, just a slow, inevitable fading. Star formation will continue for tens of billions of years yet, but the glory days are behind us. We are living in the aftermath of peak cosmic activity, and objects like 3I Atlas are the messages in a bottle from that more vibrant past, carrying information about what came before. This connects to a broader realization that has been building in astronomy for decades. The universe is not what we thought it was. It's not static, not stable, not predictable in the simple ways our equations once suggested. Dark energy is accelerating expansion when we expected gravity to be slowing it down. Star formation is declining when we assumed it would continue. And now, with 3I Atlas, even our understanding of the small-scale visitors to our own backyard is being upended. The pattern is clear and humbling. Every time we look closer, the universe surprises us. Every time we build a better instrument, we find phenomena that don't fit the old models. The lesson is humility. And that lesson extends beyond astronomy. If the universe at its largest scales is behaving in unexpected and complex ways, why should we expect the smaller scales to be simple? Why should a single interstellar object conform meekly to our predictions? The connection between the macro and the micro isn't causal, but it is deeply philosophical. Both point to the same truth. Reality is richer, stranger, and more layered than our current theories can capture. We are always playing a glorious game of catch-up, always revising, always learning that what we thought was solid ground is, in fact, shifting beneath our feet. The Euclid findings about star formation decline are a reminder that the cosmos has a history and a future, and we are witnessing a specific fleeting chapter. 3I Atlas is part of that same chapter, a visitor from another part of the story, carrying clues about where the galaxy has been and where it's going. Both tell us that nothing lasts forever, that change is the only constant, and that our moment in cosmic history is precious, fleeting, and worth paying attention to. But the surprises don't stop with star formation. Another, even more fundamental pillar of modern cosmology is now also under fire: